Hello, this is Mrs. Schroeder. We're going to begin section 2, which is systems at equilibrium. Today we're going to talk about our equilibrium expressions and how to write reactions with them in order to perform calculations like concentration. What is the concentration of something in a solution? We will cover this KSP expressions in another video. We learned already that reversible reactions reach an equilibrium when the concentrations are constant. At a point when they do not change, no matter how long I go on this graph, the concentrations would be the same for A and for B. So how could I figure that out? I was given a concentration of A of 0.3. B started out at 0. How do I know what this endpoint is? And is there a way to actually predict it? And the answer is yes. In chemistry, there's always a way. This way is called the equilibrium constant, or KEQ. It's a constant that shows a mathematical relationship between the concentration of products to the concentration of reactants. And I can't write out a cute expression for this because the expression will depend on the actual reaction. And I'll show you how that works in a minute. Couple things, it is unitless, okay, so no units for KEQ. It does depend on the temperature. Usually we report it KEQ at a given temperature. So you could look up temperatures of 25 degrees Celsius or 298 K, and you would find tables listing the KEQ expressions at different temperatures. Maybe KEQ is one thing at 25, but if I increase the heat to 100, I've changed the KEQ. So I look that up and I find out what the temperature I need to get my reaction to go the way I want it to go. I can figure it out experimentally, like we did in this table. They put the two things together, they measured it over time, and they could see eventually it got to an equilibrium point where they're not changing. So that's one way to do it. If you don't want to do it experimentally though, there is another way. So I can write the expression for KEQ. Make sure you have this written down. You will need to know how to do this in class. First thing is it has to start with a balanced chemical equation. So let's take this hypothetical example. I have assume this is a balanced chemical equation, even though it doesn't show all the A's and B's, but we're going to use that. For our equilibrium expressions, first thing is we know that we have to have products over reactants. Products over reactants. KEQ equals. Okay. So we're going to look at the concentrations of them. Concentrations of solids and liquids are left out. So don't put solids or liquids in the expression. Only things that are aqueous or things that are gases are things we're going to be concerned with. So I'm looking at these. Aqueous, aqueous, aqueous. I'm not going to include this one because it's a solid. So if I'm writing the expression for this, I'm going to write KEQ. So product is my D, and I use these brackets to indicate I'm looking at concentration of D over A and B. But I'm not done yet because I have to do something with the coefficients. In order to complete them, I'm going to use the coefficients as the power of each expression. So D had a coefficient of 4, D to the 4th power. A has a concentration of 2, A squared. B has a coefficient of 1, so I'm going to leave that as a 1. So this would be my equilibrium expression for this. I could figure out what the concentration of A or B would be if I'm given a certain concentration of D, or vice versa, if I know what KEQ is already. If you have an aqueous equation, again, this is another way to express it, where N goes with N, M goes with B, X goes with C, and Y goes with D. So it's just kind of another way of showing you how it should work. The KEQ will show if the reaction is favorable. Favorable meaning it wants to go, it wants to react, it's spontaneous, it wants to go one direction. So a favorable reaction has a higher concentration of products, resulting in a large KEQ at equilibrium. If KEQ is small, that means that the denominator is going to be larger than the numerator, and I would have an unfavorable reaction. So here's how it works. If KEQ is 1, I have an equal number of, reactants are yellow, products are green or purple. If KEQ is 1, again, they're equal amounts. If KEQ is a small number, the 0.02 is small, that means I have lots of reactants, but not much products. This would be an unfavorable reaction. Because not much of it is going, it wants to stay as the reactant. Over here I have a favorable reaction because I have lots of products, but the reactants are very small. There's not many reactants left. As a quick example, if I had this expression for nitrogen plus hydrogen goes to NH3 ammonia, the KEQ for this is actually a very large number. Notice the 10 to the 8th value. It's a very, very big number. This reaction would be very favorable because it's a very large number. Contradictory, we have the reaction of oxygen and nitrogen, which gives nitric oxide, nitric monoxide, which thankfully is a very small number, which we would say is unfavorable, not favorable. We call it unfavorable reaction because it's got a very, very small number. And I say thankfully because that's very toxic and we don't want to breathe it. So, quick example before we go. How do I write this expression? KEQ equals, I want to look at products divided by reactants. So my products are my HCO3 minus, put the brackets around it, and H3O plus, put my brackets around. This means times, multiply them together. Divided by, I have my H2CO3, and if you notice, water is a pure liquid, so it's not included in the expression. There's no concentration given. So when I put the numbers in, it gave me my acid is this, which is 3.3 times 10 to the negative second. That's my acid. Okay. The bicarbonate ion is this, so the 1.19 times 10 to the negative fourth. And my H3O concentration, hydronium ion, is this, 1.19 times 10 to the negative fourth. So when I take 1.19 times that, divided by this, 3.3, I'm going to equal 4.29 times 10 to the negative 7. This would be KEQ for the following reaction at the given or determined temperature that it is. We'll try some more problems in class and go over those with you. Also learn how to calculate concentrations when we're given a KEQ. So we'll do some of those practice problems on the worksheet. Again, make sure you have written down and listed the steps that I'm going to use. Be comfortable understanding how to find a coefficient as a power and being able to do something to the fourth power on your calculator. It's one of those little tricks of learning math. So we'll talk about some more examples in class and see you tomorrow.